In this video, we're going to take a look at section 6.2, chord properties. So, I don't know why my arcs aren't coming through here. All right, so for our warm-up, we're going to take a look again at central angles and interpreting arc measures through circles. So recall that a central angle is an angle whose vertex is the center of the circle. And a central angle's measure is equal to the measure of its intercepted arc. So if we look at this picture, for example, Z is this arc here, arc DC, and it is intercepted by angle DOC. So those things have the same measure. We know that arc AC has a measure of 130 degrees. So that means from here to here is 130 degrees. And that tells us that's going to help us find the measure of arc AB, because arc BC has a measure of 48 degrees, which means X is also 48 degrees. And if I take 130 minus 48, that is going to help me find the measure of arc AB, which is then also the measure of angle AOB, which is Y. So that was 82 degrees. Okay, just going to erase this for a second. Looking at this picture again, we see that angle AOD has a measure of 110 degrees, which would be the measure of arc AD, which is W, would also have a measure of 110 degrees. And then looking at this, so arc AD is 110 degrees. Arc AC is 130 degrees, and the full circle is 360. So to find Z, we take 130 plus 110, and then subtract that from 360. So in this problem too, we're just going to, in this section, we're also going to define inscribed angle. So again, just want to make sure we know what an inscribed angle is. It's an angle whose vertex is on the circle, like B, and whose sides are chords. So for example, angle ABC, that is an inscribed angle. Angle BCD, that is an inscribed angle. Angle ECD is an inscribed angle. And again, I want you to think back to intercepted arc. So arc AC is intercepted by angle ABC, and arc BD is intercepted by angle BCD. So again, think about extending those rays, and it's like the arc in between those rays. Just wanted to remind you of that definition. So we're going to look at chords in their central angles. We're going to construct a large circle, label the center O, and construct two congruent chords. So I'm going to help you through that. So in this space, again, pick a point for your center, take your compass, put your stylus on the center, and draw your circle. Again, yours will look a lot better than mine. Looks not too bad. So we're going to construct two congruent chords. And here's the way we do this. Take your compass, pick a setting, and you want it to be smaller than the diameter of the circle, because if you pick the diameter of the circle, you won't get chords. So usually what I like to do is I like to pick a point here, go ahead and open my compass and swoop it so that I get another point on the circle. So I took my compass, I put the stylus here, I drew an arc, and that's my intersection point. Keep your compass at the same setting. Find another point on the circle and go ahead and swoop your compass so that you get that second point. And then use your straight edge and connect the different points that you've created. So this is going to be a chord, and this is going to be a chord. And these chords are congruent because your compass was set at the same setting for both. Now what we want to do is label the one chord AB and the other chord CD. And this, remember, is our center. And so what we're going to do is we're going to construct radii to the endpoints of each of our chords. I want you to take your protractor and, oh, I don't know where that came from. There we go. And measure angle BOA and measure angle COD. So remember, put your protractor here, line it up with the vertex. Go ahead, you might need to extend one of the sides if you need to, sides of those angles. And what you should discover is that these angles are congruent. So this means if two chords in a circle are congruent, then they determine two central angles that are congruent. I want to walk you through this real quick, so see if this makes sense to you. Remember that the chords were congruent. So this segment is congruent to this segment. Remember that all radii are congruent. So this segment is congruent to this segment, is congruent to this segment, is congruent to this segment. And looking at that, these two triangles, triangle AOB and triangle COD, are congruent by side, side, side. So it's coming back to those triangle congruent shortcuts. Those are laying the foundation for all of the other conjectures that we know. And if we can see those congruent shortcuts, we can really make sense of everything that we're looking at. So that's why it works. Okay, so you could fold your circle if you wanted in half. If you would fold this side of the circle, like this half of the circle over top, these two angles could overlap and you could check your conjecture again. So this also means, remember, that the measure of an arc is defined as the measure of its central angle. If the central angles are congruent, then the arcs are also congruent. So a kind of a one-off from this is if two chords in a circle are congruent, then their intercepted arcs are congruent. So let's go back to our picture real quick. So again, what that means is that arc DC is congruent to arc AB. And then again, that's because the chords were congruent. So that means the central angles are congruent, which means the intercepted arcs are congruent. Let's take a look at some conjectures here. So in this first example, we want to find W. W is the measure of this angle here. Okay. Looking at our picture, we have this chord is congruent to this chord, which means this central angle is congruent to this central angle. So W is 70. That was a pretty direct application. This one is a little bit, we need to kind of think through things a little bit more. So we still have these congruent chords, which means this arc here is congruent to this arc here. Now we don't have central angles here, but this is the second conjecture that we looked at. So this is also 128 degrees. The question is, what is the measure of Z, which is this arc here? So notice how from here to here is 128, here to here is 20, and here to here is 128, and the full circle, again, is 360. So we're going to go ahead and add everybody up here, and then subtract from 360 to find Z. And that's going to be 84 degrees. Okay, so now we're going to look at chords and the center of the circle. So you could use some patty paper here, but I think we can do the compass and straight edge. So we're going to, on the next page, construct a large circle and mark the center, and we're going to construct two non-parallel congruent chords, and then construct the perpendiculars from the center to each chord. All right, so let me walk you through this. Okay. Mark your center. Take your compass. Draw your circle. Okay. We're going to do the congruent chords exactly the way we did last time. So again, pick a spot on your circle. Swoop your compass. Find an endpoint. Make the chord. And then do it again, but we don't want them to be parallel, so I kind of maybe pick a spot over here and swoop my compass, find my point, and construct my chord. We just don't want them to be parallel. So however you can do that so that it's not parallel. So we have our two chords. And now what we're going to do is we're going to construct the perpendiculars from the center to each chord. So I'm going to walk you through how to do that. So put your stylus on the center of the circle. Take your stylus and swoop it so it intersects each side of the chord, one on each side. And then once you do that, then you're going to do your perpendicular bisector, swoop, 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 and go ahead and construct that. We're going to do that one more time. So make sense of this. Put your stylus here in the center. Open up your stylus. It has to intersect this chord, and you're going to swoop it so it hits on the left and the right. This then is going to be your segment that you're going to find the perpendicular bisector of. Swoop, 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 and go ahead and do that. So again, this segment is perpendicular to, the segment we just created is perpendicular to the original chord, and it's also passing through the center. So now what we want to do, okay, is how does the perpendicular from the center of the circle to the chord divide the chord? So now we're going to look at the relationship. Now we have this point marked off here. We've intersected our chord, and we're going to look. It turns out that if you measure these or use your compass, that this is actually the midpoint of the chord. So the perpendicular from the center of a circle to a chord is the perpendicular bisector. At first it was just perpendicular, and now it turns out that it's the perpendicular bisector. Okay? We're also going to take a quick peek at the relationship between the length of congruent chords and their distance to the center. Okay? So distance, remember, is defined on the perpendicular. So again, if we have a point and we have a segment, when we say what's the distance from this point to this segment, it's always the perpendicular distance. Because if you just said here, if you measured from here to here, a random point, you would get a different answer if you measured from here to here. So distance is always defined as a perpendicular, or if you notice we made a triangle, as an altitude. And that's what we call the height of a shape. Okay, so if we go ahead, remember these chords were congruent. This chord is congruent to this chord. We constructed the perpendicular bisectors from the center, and now I want you to compare the lengths. So, for example, take your compass, take your compass and put it on the center and kind of open it up here. So find this distance. And if you take your compass and keep it the same distance, you should notice this will also be the same. So that means, or you can measure with your ruler. This means that two congruent chords in a circle are equidistant from the center of the circle. Are the results the same if you change the size of the circle and the lengths of the chords? No, as long again as the chords are congruent, they will be the same distance. It also means though that the longer the chord, the shorter the distance. So for example, here's a chord, and if we look at its distance from the center, it's much shorter than if we had a shorter chord and looked at this distance. So the longer the chord, the shorter the distance to the center. I'm going to start a new video because I noticed I'm almost out of time here and I have some examples and some more conjectures. So we'll pick up in a second video.